Welcome to Instronexus with another important topic, effective alarm management. Today, we are going to walk through the comprehensive framework defined by the ISA 18.2 and IEC 62682 standards, which guides how we manage alarms over their entire lifecycle. We will dive into the alarm management lifecycle itself, a continuous improvement process that consists of 10 key stages to ensure your system remains healthy. We will also look at how to measure success with KPIs, giving you the key metrics needed to track performance accurately. Beyond the technical steps, we'll explore the benefits of adopting these standards, including improved safety, efficiency, and operator effectiveness. Finally, here is the roadmap for our discussion today. We're going to start with the basics, defining exactly what alarm management is and looking at the core problem plaguing the industry today, operator overload. We will discuss why this is critical regarding safety and financial impact. Then, we will introduce the heroes of our story, the ISA 18.2 and IEC 62682 standards. The bulk of our time will be spent walking through the alarm management lifecycle, which is the core concept you need to master. We'll wrap up by looking at key performance indicators, or KPIs, so you know how to measure success, discuss the benefits and challenges you might face, and finally, give you practical steps on how to get started immediately. So, let's start at square one. What actually is alarm management? It's defined as the set of processes and practices for designing, operating, and maintaining a process alarm system. But let's look beyond the textbook definition. The real goal here is to ensure that every single alarm presented to an operator is meaningful and actionable. If an alarm goes off, it should require an operator to do something. It's not just about silencing noise. It's about filtering information so that the human being at the console can run the plant safely and efficiently. If the system is cluttered with status updates that look like alarms, we are failing. We are aiming for a system where the operator trusts the screen in front of them. Why do we need a standard? Because we have a massive problem in the industry called operator overload. Many industrial plants suffer from what we call an alarm flood. Imagine trying to drive a car while your dashboard screams at you about the radio volume, the tire pressure, the wiper fluid, and the engine temperature all at once. That is the reality for many operators who are overwhelmed by hundreds or even thousands of alarms per day. When everything is an alarm, nothing is an alarm. This sensory overload leads to desensitization, where operators simply stop hearing the chimes, or worse, acknowledge them without looking just to make the noise stop. This is a recipe for disaster. This isn't just a nuisance. It is critical for business and safety. First and foremost, poor alarm management increases the risk of safety incidents and has been a contributing factor in major industrial accidents. Beyond safety, there is the cost of unplanned downtime and production loss. If an operator misses a critical alarm because it was buried in a flood of nuisance alarms, that can lead to a plant shutdown. Furthermore, this overload causes high stress and fatigue, reducing operator effectiveness and their ability to respond to real emergencies. Finally, when the board is lit up like a Christmas tree, it becomes incredibly difficult to troubleshoot plant upsets and find the root cause of a problem. To solve these problems, the industry developed specific standards. You will often see two names referenced, ISA and IEC. ISA 18.2 and IEC 62682 are the global benchmarks for alarm management in industrial processes. These weren't just written by academics. They were developed by a consensus of end users, manufacturers, and safety experts who wanted to create a universal language for how we handle alarms. Before these standards, alarm management was often subjective, based on whatever the current engineer thought was high priority. These standards bring objectivity and engineering rigor to the discipline. They move us from alarm management as an art to alarm management as a science. A common question is, which standard should I follow? The good news is that you don't really have to choose. ISA 18.2 and IEC 62682 are functionally identical. They share the same philosophy and establishing international consensus on principles and practices. The ISA standard originated in North America, while the IEC standard adapted it for the international stage. Essentially, adhering to one means you are adhering to both. This is important because it allows for a consistent, site-wide approach to alarm management, regardless of where your equipment was manufactured or where your plant is located. They both rely on the same core concept, the Alarm Management Lifecycle. This diagram right here is the heart of the standard, the Alarm Management Lifecycle. It is a continuous improvement process containing 10 key stages. It starts with philosophy, where we set the rules. We then move to identification and rationalization to determine what alarms we need. Then comes detailed design and implementation to build them. Once running, we enter the operation and maintenance phases. But we don't stop there. We have monitoring and assessment to check our work, management of change to control updates, and finally, audit to ensure compliance. We're now going to spend the next few minutes breaking down each of these stages individually so you can see how they fit together. Stage 1 is philosophy. This is your foundational document. Before you touch a single configuration in your control system, you must write this document. It defines roles and responsibilities. Who is allowed to change an alarm set point? Who maintains the master database? It establishes your criteria for alarm prioritization. What makes an alarm high versus low priority? Most importantly, it defines what is and what is not an alarm. If a notification doesn't require operator action, the philosophy document clarifies that it shouldn't be an alarm. This document sets the guidelines for the entire program and ensures consistency across your site. Stage 2 is identification. This is a systematic process where we identify all potential alarms. We aren't filtering them yet, we are just finding them. We look at all sources: field instruments, control system logic, and safety systems. The standard promotes a consequence-based approach. This means we identify alarms based on the consequence of no operator action. We ask, if the operator does nothing, what bad thing happens? If the answer is nothing, it probably shouldn't be an alarm. The goal here is to thoroughly document every potential alarm condition, providing a comprehensive list that we can take into the next, most critical stage. Stage 3 is rationalization. If there is one slide to pay attention to, it's this one. This is the review process where we justify the existence of every single alarm. We review the potential alarms against the philosophy we wrote in Stage 1. We assign the correct priority, high, medium, low, and we clearly define the cause, consequence, and corrective action for every alarm. If an alarm does not require immediate action or has no consequence, we eliminate it. This is where we clean up the mess. The output of this stage is a master alarm database that tells us exactly how the system should behave. Once we know which alarms we need, we move to Stage 4, detailed design. This focuses on how the alarm is presented to the operator. We look at HMI design. How does the alarm appear on the screen? What colors are used? We configure alarm sounds, making sure a critical alarm sounds different and more urgent than a low priority warning. This stage also involves advanced alarming techniques, like dynamic alarming, where thresholds might change based on whether the plant is starting up or in steady-state operation. The goal is to optimize the presentation so the operator can make informed decisions instantly. Stage 5 is implementation. This is where we take the paperwork from the rationalization and design phases and put it into the real world. This involves the physical control system configuration and building the actual HMI graphics. A vital part of this stage is testing. You must thoroughly test the new alarm configurations in a non-production environment before going live. We need to ensure the logic works as intended and that the graphics display correctly. This stage is the bridge between the theoretical design and the operational reality of the control room. Now the system is live, and we enter Stage 6, operation. This is where the alarm system is used day to day. The critical component here is proper operator training. It is not enough to just have good alarms. The operators must know what they mean and, crucially, what to do when they see them. We need to develop and document clear response procedures for different priorities. We also look for continual improvement here, reviewing operator performance and getting feedback from them to see if the system is actually helping them run the plant. Empowered, well-trained operators are the result of a good operation phase. Systems degrade over time, which brings us to stage 7, maintenance. We need to keep the alarm system healthy. This involves regular testing of critical alarms to ensure the sensors and logic are still working. It also involves fixing nuisance alarms. If a sensor starts chattering, going on and off rapidly, it needs to be repaired immediately to prevent operator distraction. We also need to regularly review suppressed alarms. If an operator shelved an alarm for maintenance, we need to make sure it gets turned back on. Maintenance ensures the long-term reliability of the system. Stage 8 is monitoring and assessment. You cannot improve what you do not measure. In this stage, we continuously collect data on alarm rates, standing alarms, and floods. We take this real-time data and benchmark it against KPIs, key performance indicators defined in the standard. Are we seeing too many alarms per hour? Is one specific tag responsible for 50% of our activations? By analyzing this data, we identify improvement opportunities. This closes the loop and helps us identify areas that might need to go back through the rationalization process. Stage 9 is management of change, or MOC. This is the shield that protects your rationalized system. We need a formal change control process. We cannot allow just anyone to add a new alarm or change a set point because they feel like it. Any change must be reviewed and approved to ensure it aligns with the alarm philosophy. We must document the details of the change, why it was made, and the impact it will have. And crucially, we must communicate and train the operators on this change. Without MOC, your clean, rationalized system will degrade back into chaos within 6 months. The final stage, stage 10, is the audit. While monitoring happens daily or weekly, the audit is a periodic, formal check, usually done annually or every few years. The goal is to verify that the entire alarm management program is being followed. Are we adhering to the philosophy? Is the MOC process being used? Are operators actually trained? We evaluate the effectiveness of the system against our performance targets and identify gaps. This high-level review ensures that the program doesn't stagnate and continues to drive improvement over the life of the plant. We mentioned monitoring earlier, but what numbers should you actually aim for? What does good look like? The standards provide very specific target values. Now, let's get into the specific numbers. How do you actually know if your alarm system is good? This slide outlines the target performance metrics defined directly by the ISA 18.2 and IEC 62682 standards. These are the benchmarks you should be aiming for. First, look at the average alarm rate. The goal is to have less than one alarm every 10 minutes per operator. This ensures the workload is manageable day to day. Next, and perhaps most critically, is the peak alarm rate, or alarm floods. During a plant upset, you want fewer than 10 alarms in any 10-minute window. Anything more than that, and it becomes nearly impossible for a human to react effectively. You also want to keep your standing or stale alarms, those active for more than 24 hours, to fewer than 5 at any time to prevent clutter. Finally, check your priority distribution. Not everything can be an emergency. A healthy system should be roughly 5% high, 15% medium, and 80% low priority. Meeting these targets is the key to a safer, more efficient control room. Implementing all of this takes work, so why do we do it? The benefits are substantial. First is improved safety. Operators can identify and respond to critical situations effectively, preventing accidents. Second is increased efficiency. By reducing downtime and smoothing operations, you save money. Third is regulatory compliance. Insurance companies and regulators increasingly expect these standards to be followed. And finally, better operator effectiveness. We reduce stress and fatigue, leading to a happier, more focused workforce, capable of making better decisions. It is important to be realistic. This is a journey, and there are common challenges. The biggest one is often cultural change. You have to shift the mindset from more alarms is safer to the right alarms is safer. Resources are another hurdle. This process requires time from your best operations, engineering, and maintenance people. Legacy systems can also be difficult. Older control systems might not support advanced alarming features or easy auditing. And finally, sustaining gains without MOC and maintenance. It is very easy to backslide into bad habits. If you're ready to get started, here are your first steps. First, Form a team. You need a cross-functional group. Operations, engineering, and maintenance must all be at the table. Next, develop your philosophy. Write the rulebook before you try to fix the alarms. Third, monitor performance. Install software or just use spreadsheets to track your current alarm rate so you have a baseline. And finally, try a pilot project. Don't try to fix the whole plant at once. Pick a small, contained unit, rationalize it, and prove the value to the rest of the organization. To wrap up, remember that alarm management is a continuous journey, not a one-time project. It requires a strong philosophy, rigorous tracking of metrics, and a commitment to maintenance. But the reward is a plant that is safer, more efficient, and easier to operate. Thank you for watching. If you found this guide on ISA 18.2 and IEC 62682 helpful, please leave a like and subscribe in Strunexus for more content on industrial automation. See you in the next video.